Welcome back to lecture 14 of CSE 31, part 2. So in the last part, we talked about how to encode branch instructions into I format. And we just mentioned that the immediate for branching is just the number of instructions counting from the next line of your branch instruction. So again, is the count between the destination and your PC plus 4. So just remember that. Okay, so in this section, we're going to talk about the last format, which is J format. Okay, so in J format, give me an example. What is J format? J, right? J and then the label, or JAL if you want to call a function call. So by now, hopefully you can tell the difference between J and JAL. Okay? With J, you are just going there. That's all. It doesn't do anything else. But with JAL, you not only go to that label, but you also save the return address into RA. So only use JAL for function call, okay? Because when you're at the end of the function, you will need to go back. So you need to use JAL to store the address. Okay? So this is branch in the lecture slide. So with J and JAL, our idea is that we can use these two instructions to jump to different parts of the memory, right? But the problem is, again, address is 32 bits, right? And how many bits do you think we can have in the instruction to store the address? So remember, this is J format, right? And doesn't matter what format of instruction, we still need one opcode, right? So how big is an opcode? Opcode is 6 bits, right? So which means that even if we don't need any registers, we still need the 6 bits for opcode to tell us that this is a J or JAL. So now I have 32 bits of instruction and I use 6 bits for opcode. How many bits left? I have only 26 bits left. But the problem is now this is not branch, which means that we are not describing how far it is, because sometimes your function can be far, far, far away from your main function. Then it doesn't make sense to count the number of lines apart, right? So the question is, how can we describe 32 bits into 26 bits? Okay, so, and we just mentioned that opcode is just the 6 bits. So I think for J is 2 as opcode, and JAL will be 3. That's all. J format only contains these two instructions, J and JAL. You may ask, what about JR? JR is not J format because it takes in a register. So JR is actually R format. If you look at the MIP sheet, you can find out the detail. Okay, so now the question is, how can we specify 32-bit address into 26 bits? We just cannot, because this is beyond physics, right? So, but what kind of information we know? As we describe that in branch, each instruction is one word, which means that the address of each instruction should end with 2 zeros. Okay, so because of that, we can save 2 bits from these 32 bits. So which means that we can remove these 2 bits because it's redundant. We don't need to know that. Okay. So in a sense, we can specify 28 bits of the 32 bits. Okay. But the thing is, what about the missing 4 bits? What can we do? Okay, so we're kind of taking a stretch here now. Okay, so yes, our goal is to be able to jump to anywhere in the memory. Okay. But in reality, we cannot do this because of the limitation of the 28 bits available, okay, for the instruction label. So what can we do? We assume that the distance or the address that we jump to will have the same leading 4 bits of our current PC. So what does that mean? Let me go back to notes. Okay. So I'm going to share my OneNote notes online too, so that you can also take a look at this note instead of using the whiteboard function from the video. Okay, so we have an address, right? So for example, I have J label, right? And let's say the label is far, far, far away. Okay, and we have the PC here pointing at this, right? And the address will be 32 bits. And with the label, I also have an address of 32 bits. Okay, so what we assume is that when we take the jump, these 4 bits will remain the same. So essentially, we are jumping the distance of at most 28 bits only. That's all. Okay, so this is how we make the assumption. So technically, J and JAL won't take us to everywhere in our memory, which is fine. We're going to talk about what if the branch or the jump distance is further than 28 bits. Then what can we do? We can work things around. So stay tuned. Okay. So from now we can see that all we need to do is giving you a jump statement, right? LABEL. I have my opcode and then my 26-bit address, right? All we need to do is take out this 26 bits and then add 20. Okay, let me write it clear, 20. And then put 4 bits, which is the first 4 bits of PC. Okay, so PC points at here, right? So basically, based on what your address is, okay, your current address, take the first 4 bits and put that as the first 4 bits of your target address. And then you add 2 more zeros at the end, and now you have your label address. Sound good? Okay, so this is how we create or to translate any J format instruction into zeros and ones. All you need to do is take out the 26 bits and then add the 2 bits at the end and copy the first 4 bits of your current address. And that's your final target address. Okay? Okay, so let's go back to the slides. Okay. Am I sharing? Let's stop it and then do it again because I can't really. I'm not really sure. Okay. So now let's go back. Okay. So now we know how we can encode the J format. So again, it doesn't really allow us to jump to anywhere anymore because we can only at most jump to 28 bits apart. But that's good enough because most of the program won't need us to jump that far, okay? Because think about 2 to the power of 28 is really big, okay? And as long as your program is less than 256 megabytes, you should be fine. So don't worry about that, okay? And even if we want to jump beyond this boundary, we can always use absolute address by saving your address into a register and use JR. So with that, you just store the 32-bit address into a register, and then you just use JR, and you have the same result. Okay, so don't worry about the limitation of the 28-bit. It should be fine. Okay, so here is an example. Again, your new PC, the target PC, will be the 26-bit address truncated with 2 more zeros at the end, and then the first 4 bits, bit 28 to 31, the left foremost bits or the most significant bits of your PC. When you combine these bits together, and that's your final target. Okay, so make sure that you understand where these portions come from. Okay, all right, so for example here, I have my 26-bit target address encoded into the instruction, and then I add 2 more bits. That's why the final address ends with 00. And then you copy the first 4 bits of your PC and put that in front of the final PC address. And now this is your actual target address. Okay. All right, so now let's review. If, again, when I want to combine 2 C files, and the files contain a jump statement and a branch statement, let's say. So now, since I combine the 2 files, which means that these instructions will be stored in different addresses now. Okay. So the question is, will jump require any change? So when I have the jump statement in the instruction, okay, just like the one that I show you in the OneNote, okay. So do I need to change the target address, okay, when I combine the files? Okay. The second one, branch, do I need to change the immediate after I combine the files? What do you think? Okay, so now let's go back again to my OneNote. All right. So for jump, oops, I should use for jump is what? I have opcode and then the address, right? With 26 bits. So the question is, when I move this instruction into a new file or combine it with an existing file, do I need to change this address? What do you think? Would this label remain the same old address? Of course not, right? Because if I have J label, okay, somewhere in my program, my label is here. Okay, I have my address here. Would this address be the same if I move this code into another file? Yes, definitely, right? So that's why if we combine files, the compiler will modify this portion according to the new address of this label. So keep that in mind. Okay. So yes, we need to change the address. What about branch? Well, branch, we just had an example from the last part of the lecture, right? So let's go back to branch. I should keep them in one file actually. Okay, so for branch, remember BEQ, let's say, okay, R1, R2, label, right? So let's use an example here. My label is here. So which means that what is the immediate? Remember how do we count that? Starting from this line, PC plus 4, right? And then how many lines apart? 1, 2, 3, 4, 5. So immediate equals to 5. Okay. So now the question is, when I copy this chunk of code into a new file combined with another existing file, do I need to change this file? The answer should be no, right? Because we are not changing the structure unless you add new lines in between. Otherwise, this 5 remains the same no matter where you put that in. So that's the difference between what we call absolute address for jump statement and relative address for branch statement. Okay, so this is jump instruction. Okay, so again, if you have any questions, make sure you email me, and I will also have Zoom online office hours soon. Okay, so the answer is false and true. So for jump, you have to change your address. But for branch, you don't need to, because the branch already encodes the differences between the destination and your original location. Okay, so this is a summary. So we have covered all 3 formats. So basically, from now on, you should be able to convert every single instruction from MIPS to zeros and ones, and backward too, from zeros and ones to MIPS code. Okay, I will pause the lecture here, and then we'll resume the third part in the next video.